So I'll start with a quick brief introduction. Welcome everybody. It's my pleasure to introduce Jessica Lee, who is coming here virtually from UCLA, where she's an associate professor in the Department of Statistics. And Jessica is going to talk about Clipper, which is an FDR control method. So Jessica, I'll let you take it away. Thank you.
Thank you for the introduction, Walter, and thank you for having me here. So today I'm going to introduce a recent work done by my two PhD students, Shinjo and Yiling, who are also here. And this work is for the multiple testing problem, a classical problem that has been investigated for more than 20 years. Why do we want to investigate this? I'll give some motivations, but the primary reason is that we found that even though we are so familiar with controlling the FDR by using p-values, however, it is actually very difficult for biological data analysis for various reasons. So to start, the background is that we look at high-throughput biological data analysis. By high-throughput, we mean that we measure many features. So we call this a high-dimensional problem, and we have a small sample size. So in biological studies, this is usually the number of replicates. Due to the expensive costs, the replicate number is not big, usually no greater than 3. And we often compare two conditions. And we call one condition as the experimental condition, the condition of our interest, and the other condition as the background or negative control condition. So the interesting features are going to be identified. But what do we mean by interesting? So I'm going to give 4 motivating examples. One from the ChIP-seq data, one from the mass spectrometry data, one from RNA-seq data, and one from High-seq data. They are all called as high-throughput biological data in the genomics field. So for the ChIP-seq data, this is a diagram showing that here we often have just 2 tracks as this, and one from experimental condition, one from background condition. Before the analysis, we need to divide the whole genome into bins or genomic regions. So this is one region. And for this region, we're going to get 1 count from experimental data, 1 count from background data. So the problem is to compare the 2 counts and then call this region as interesting if the experimental count is much larger than the background count. So that's the setup. And for mass spectrometry data, this is the raw data, which is called mass spectrum, 1 window for 1 spectrum, but this spectrum is not directly usable. We need to convert the spectrum into a peptide sequence. And to do that, we have a protein database. You can see that in the database, we have those short peptide sequences. What we're going to do is to align each spectrum with each sequence and call it a peptide spectrum match, short as PSM. And for this PSM, we're going to get a matching score. But we're not sure if the matching is really biologically meaningful or just random matching. So as a negative control, people just inverted the peptide sequences each and call this decoy protein database. Presumably, the sequences here are not real, they are just false sequences. So if we align the same spectrum into the decoy database and find the decoy PSM, that PSM score will serve as a negative control. So in other words, for every spectrum, it will have a target score and a decoy score. So we only want to trust the target match if its score is much greater than the decoy score. That's the setup for this problem. For the third application, which is very widely used in transcriptomic analysis, so-called differential gene expression analysis. So here we have every column as a gene and every row as a replicate. Here we have 3 replicates per condition. And for every gene, essentially, we're going to compare its 3 values from each condition and see if there are significant differences in our statistical way of saying. But the difficulty here is that we have only 3 replicates per condition. So the sample size is very small, but we have many genes. In the fourth example from High-seq data, the question is similar. So here we look at genomic region pairs. So you can imagine this as the upper triangle of a contact matrix. By contact matrix, we mean that here the rows and columns are genomic regions, and every entry, say the ijth entry, is the interaction intensity between the ith region and the jth region. So here we're just drawing a block of region pairs. And the question is, does this block have very significant differences between two conditions? And in this case, we're just showing two replicates. You see that these two are from condition 1, these two are from condition 2. So it's a similar problem to the differential gene expression analysis, but here we have even more features because every feature is a pair. All right, so in the above 4 applications, we see that the interesting features are defined either as enriched or differential. So what do we mean by that? So by enriched, we mean that a feature has higher expected measurement in the experimental condition than in the background condition. So in the previous 2 examples, the peak column from ChIP-seq data and the peptide spectrum matches from mass spectrometry data belong to this type. Another type of problem is to tell the difference. So a feature is called differential if its expectations under the 2 conditions do not equal. And for the differential expressed genes or differential interacting regions, they belong to this type. So in other words, here we're looking at each feature marginally and try to decide whether we want to call this feature interesting or not. So that's a multiple testing problem. And for this problem, the classical approach is to use FDR, false discovery rate, as a criterion for drawing a threshold so we can call discoveries. The frequentist FDR was proposed in the 1995 paper, one of the most well-cited paper by Benjamini and Hochberg. And its definition is the expected ratio of false discoveries among all the discoveries. Of course, we must have at least one discovery to calculate the ratio. And this ratio is called the false discovery proportion, whose expectation is the FDR. And here the expectation is for the sampling distribution of our data. So this is a frequentist criterion. And in parallel, under the Bayesian paradigm, we have the Bayesian false discovery rate and the local false discovery rate and the local false sign rate. So for these criterion, we are basically considering our data to be conditional on, and then we want to calculate the probability of making false discoveries. In my talk today, we will focus on the frequentist FDR. So this is a recent review paper, benchmark paper, published in Genome Biology. It is a top-tier journal in the genomics field. So this paper benchmarked several FDR control methods with applications in computational biology. And we can see that the 2 most widely used methods, the Benjamini-Hochberg, short as BH, or John Story's p-value method, these 2 only take p-values as input. And then they will set a threshold on the p-values to call discoveries with a target FDR control. And later, there is a method called IHW, independent hypothesis weighting. It has used additional information from feature covariates, which are assumed to be independent of p-values to boost the power. So in our talk, we focus on these approaches because they're very general. They only require p-values as input, and they're widely used. So I said a large class of FDR control methods are p-value based. In particular, the 2 that only require p-values are the BH and the Q-value method. The local FDR-based method is another type of method. Although its root is in the Bayesian diagram, but still it can approximately control the frequentist FDR. So we'll also consider this type of methods in our comparison. All right, so what issues do we have for p-value based methods? So to calculate a valid p-value, we need either a valid distribution assumption if we're doing a parametric test, or we need a large number of replicates, a large sample size if we're going to do a non-parametric test. And with either types of tests, in the context I introduced before, the 2 condition comparison, the p-value calculation approaches can be categorized as either paired or pooled. I'm going to introduce each. What do we mean by paired? So paired is essentially a 2-sample testing problem. For each feature, we're going to compare its measurements under the 2 conditions and summarize its measurements into a p-value. So let's say we have D features, and here each row represents a feature, and the first few columns is from one condition, the last few columns from another condition. So for this row-wise comparison, we're going to get 1 p-value per feature. And then we need just to use the BH or the Q-value procedure to set a cutoff. The issues with applying this approach is that sometimes in computational biology, the test is misformulated, as we'll see. Sometimes people misformulate this 2-sample testing problem as a 1-sample testing problem. The second issue is that people may misspecify the model, the parametric model, such as mistakenly assume a negative binomial as a Poisson distribution. So this is a famous example, a very popular bioinformatics tool called MAT. It's for calling peaks from ChIP-seq data, the example I showed before. And this paper has been cited for more than 8,000 times. So it's one of the most successful softwares. And if we read the method section, we'll see that the way it calculates a p-value is to first, for each region, define a lambda parameter for the null distribution. So I'll just leave out the detail for the lambda parameter estimation. But essentially, they use both the control data and some of the experimental data to define this lambda. And this lambda, although it's an estimate from data, but they essentially treat it as the true parameter of the null distribution. Then with this lambda, they will calculate the p-value for this region based on the experimental count, put it into the Poisson distribution, and treat the right tail probability as the p-value. So you can see that by ignoring the uncertainty in the lambda estimate, they are essentially converting a 2-sample testing problem to a 1-sample testing problem. And I was very confused when I read this paper during my graduate school back in 2008. I was wondering, how could this p-value be valid? But then I realized, oh, this issue is actually not just for this paper in particular, but it's very prevalent in many papers in the field. So this gave me a strong motivation to investigate whether we can get around the need to calculate valid p-values to control the FDR. Okay, that's the paired approach. For the pooled approach, this is widely used for peptide identification from mass spectrometry data. So by pooled, we mean that we pool the features together. So in this approach, let's just simply assume, okay, the summary statistic is the sample average, sample mean. So for each feature, we get its mean from the experimental condition on the left. We also get their sample means from the background condition on the right. So then we pool the D features background means into a null distribution. And we call this distribution the one we're going to use for p-value calculation. Then for each experimental average for each feature, we pool those features into the distribution. And again, we call the tail probabilities, whether it's one-sided or two-sided, as the p-value. So, and here in the assumption here is that all the D features have the same distribution under the background condition. This is something we call a homogeneous background. But this assumption needs to be verified before use. However, we figure out that this is often just assumed without justification. So if this homogeneous assumption doesn't hold, then the p-value from this approach would be problematic. All right, so I just introduced the two ways paired or pooled for p-value calculation, and then BH and Q-value procedure will be applied for calling discoveries. The next class of method, local FDR-based methods, will also be used in our benchmarking. So I'm going to introduce it a little bit. So the local FDR method was proposed by Efron in 2001. So the key idea here is that it wants to estimate the local FDR of feature J. And it's defined as the probability that a feature is uninteresting, given that the feature's statistic is taking the value of the statistic of the Jth feature. So Zj is the observed statistic for Jth feature. And if this random statistic takes this value, conditioning on that, what is the probability that a feature is uninteresting? And this local FDR is connected to the Bayesian FDR in the way that they differ in the conditioning. So in Bayesian FDR, the condition is that the statistic takes value more extreme or equal than the observed statistic. And what's the probability that this feature is uninteresting in? All right, so we can show that if the statistic is informative, then we could imagine that the local FDR is monotone in the statistic value. If that's the case, then we can show that thresholding local FDR at value Q, let's say 5%, can make sure that the Bayesian FDR is under Q. And then the Bayesian FDR itself can be regarded as an empirical estimate of the frequentist FDR. So that's why we say by thresholding local FDR to Q, we can approximately control the frequentist FDR under Q. But this is not exact, unlike the BH procedure or the Q value procedure. So then the question is, how do we compute a local FDR for feature J before thresholding? So there are two ways. One is to assume that the null distribution, so-called as empirical null by Ephron. So assuming the null distribution is a normal distribution, and we're going to fit this normal distribution from all features statistics together. And the second approach is to numerically obtain the null distribution by swapping replicates between the two conditions. But this swapping approach will require that we have at least 2 replicates in one condition for the differential analysis. Otherwise, if it is 1 versus 1, then for differential analysis, swapping doesn't make a difference. So the swapping approach will not be applicable. Okay, this is our proposal, ChIP-seq. So the goal of our proposal is that we don't want to rely on p-values for FDR control. We don't want to assume parametric distributions for the data. And we also don't want to require many replicates. And the name actually came from this idea that we are trying to clip off a small number of features as interesting. And also because of the famous MBA team LA Clippers, so we think this name may be relevant and easy to remember. So ChIP-seq has 2 components. One is what we call the contrast score. So you can consider this contrast score as a summary statistic for every feature, and it's informative for contrasting the 2 conditions. And the second component is a cutoff. So we need to set a reasonable cutoff on the contrast score to call discoveries. For this purpose, we leverage the recent advances from the knockoffs literature, from the Barbers and Candace first paper, we call this BC procedure, and later a multiple knockoff paper by Gimmels and Doe called GZ procedure. So please be aware that the difference between knockoff and our work here is that we don't do joint modeling. So we're not doing this multiple testing in a multivariate modeling scenario. We're just doing marginally for each feature. But we think that their thresholding procedure here is very useful for our work. So we borrowed their procedures for the cutoff part. And as a result, we hope that our work will be robust to the data distribution, number of replicates, or even the existence of outliers. Okay, so this is the illustration of what we do. So given the contrast scores, so we do that for calculate 1 per feature, we get D contrast scores. So this shows the empirical distribution of the D contrast scores. So as we'll see later, we want the contrast score to follow one important property. That is, for the uninteresting features, we want their contrast scores to be symmetric about 0. And for the interesting features, we want their contrast scores to be very positive. So with that, then we want to find the threshold on the contrast scores and call the features whose contrast scores are on the right of the threshold as discoveries. And this is the formula from the BC procedure, and I will introduce this in detail later. All right, so formally, notation-wise, we consider D features, and we denote the J features measurements in the experimental condition as the m-dimensional vector. So we assume there are m replicates under experimental condition, n replicates under the background condition. And as the case for most biological data, all the measurements are non-negative. And an important assumption we assume here is that for each feature under each condition, the m measurements are IID with the same mean. And the n replicates are also IID with the same mean. So we denote the means as mu xj and mu yj, j from 1 to b. So we want to call feature j interesting in differential analysis if mu xj is greater than mu yj. In differential analysis, we want to call the feature interesting if mu xj is not equal to mu yj. Okay, so what's the key assumption in our procedure? So the first thing is that we need independence, as we just said. So for the M features and N features here, they must be mutually independent. So what do we mean by that? Look at the right. So let's say gene 1 is one feature, gene 2 is another feature. Let's say we have 3 replicates in one condition, so we're plotting one condition. So if these 2 genes share the same mean, and if their random deviations from the mean are independent of each other, then we saw this is the case when our assumptions hold. But sometimes we see the data like this. So gene 1 and gene 2, the measurements are the 3 blue dots, blue triangles. So on the surface, we see that the 2 genes have a strong correlation. But in many cases, this may be due to the fact that these 3 measurements have 3 different expectations, and the expectations are correlated. So if that's the case, then we need some batch correction in the beginning. That means we need to adjust the 3 samples, 3 replicates, so that the same gene's mean, the same gene has the same mean, same expectation in the 3 samples by aligning the data and then apply our procedure. So this is one way to explain what the independence means. And also for the uninteresting feature J, if it's uninteresting, then we basically need to assume that this feature J's M and N measurements from the 2 conditions are IID. They cannot be distinguishable. Okay, so now I'm going to introduce how our method is designed for 3 different analysis tasks. Enrichment analysis with M equals M, the same number of replicates. Enrichment analysis with M doesn't equal M, and differential analysis. So the reason we want to distinguish the enrichment analysis with M equals N and M doesn't equal N is because for the former, we can naturally use the background replicates to be our negative control, just like our knockoff. But for the second case, when M doesn't equal to M, we need to use permutation to create a negative control. We cannot simply use the background replicates as they are, and we'll see this later. So the simplest case to start with, enrichment analysis with M equals M. How can we make sure the feature has, we capture every feature's contrast between the 2 conditions? For that purpose, we design 2 summary statistics. One is what we call the difference. That is, we take the sample means and their difference. So you can see that if the sample mean difference is positive, then we know, okay, in the experimental condition, probably the feature has higher expression. So roughly like that. So therefore, the sign is informative in the difference statistic. And the second one, maximum statistic, what we basically do is to take the maximum. Please note that here we don't need absolute values because they are all non-negative. So we take the maximum of the 2 sample means and we multiply by a sign depending on which mean is greater. So still here, the sign of the maximum statistic will be meaningful. So in the enrichment analysis with M equals M, we will just use the contrast scores as we'll just define the contrast scores as the 2 statistics like this. And here is the illustration. So for enrichment analysis with 1 replicate per condition, in this case, this is the interesting feature. So the difference will be 10 minus 0, that's 10. The maximum will be 10 times positive sign 10. For this uninteresting feature, difference is 1 minus 2, negative 1. Maximum, it will be 2 times a negative 1 sign because the background is greater than the experimental, so we get negative 2. So this is how we calculate the contrast score. And with this definition, we can show that the contrast score will satisfy the conditions required by the Barbara-Candice procedure, which will be next slide. So what does this procedure do? This procedure will take the non-zero contrast scores and their absolute values. So these will be the candidate threshold on the contrast score. Among these candidate thresholds, we pick the smallest positive threshold such that we have this ratio controlled under Q. And you can intuitively think of this ratio as the false discovery proportion. But because of the theory behind the procedure, we can show that this can lead to exact FDR control. So in the numerator, it's actually the number of contrast scores that's less or equal than the negative t. So that's the mirror of this threshold on the left-hand side. That number plus 1, that's the numerator. The denominator is the number of discoveries we'll call. So that's the number of features on the right of the threshold with the maximum taken with 1. So to avoid the dividing zero issue. And for this ratio, if we set it to Q and we find the smallest t we move this from the right to the left, find the smallest t, so the ratio is controlled under Q, and we stop there. And then this t will be used as a threshold. We call TBC. Then we use TBC to cut off the contrast scores. So for all features whose contrast scores are greater than TBC, they will be called discoveries. So in this paper, it did a comparison between the BC procedure and the BH procedure when both use p-values. And it showed that BC procedure is more robust. Although here we didn't apply BC procedure to p-values, but that's possible. It's just here that we want to get rid of the p-value, so we just define the contrast score and directly apply the BC procedure. So this is the key lemma that needs to have the BC procedure valid. And we can show that the two ways we define our contrast scores, the difference and the maximum, can satisfy the 3 conditions. So here we call the sign of the contrast score of J's feature as Sj. So it takes value -1 for negative contrast scores, 0 for 0 contrast scores, and 1 for positive contrast scores. And we denote the unknown set of uninteresting features as this Metcalfe n. And then the assumption is that these signs are mutually independent. This is due to our independence assumption. And for the uninteresting features, also because of our assumption, it will take value 1, the sign will take value 1 or -1 with equal probability. And finally, we want for the uninteresting features that their signs are independent with the absolute values of their contrast scores. Okay, so we can show that when m equals n, all the 3 conditions hold. So we can apply the procedure we just described. But for m doesn't equal n, for the enrichment analysis, the 2 and 3, these 2 conditions will no longer hold. The reason is that if we consider the sample means from the 2 conditions, when the 2 conditions do not have the same sample size, then their sample means will not have the same variance, and that will cause issue here. So to address that issue, we need to create some negative controls by permuting the data. This is what we do. So let's call this matrix W. The first m columns are from experimental condition, the last n columns from the background condition. We define sigma as a permutation of the columns. So after the permutation, we still call the first m columns the new experimental condition, and the last n columns the new background condition, but we know that it's not really true. So for the permuted measurements, we will still denote each jth row as xj sigma, yj sigma, and j go from 1 to b, the rows. So let's say that we consider H permutations. So later we'll discuss how this H is going to be chosen, but I would say for now, this is still an open question. So we consider the original data as the identity permutation denoted by sigma 0. And for the H non-identity permutations, we call them sigma 1 to sigma H. So together, now we have H plus 1 data sets. So for each feature, we need to define its degree of interestingness from each data set, identity or permuted. So here we just take the difference statistic as the degree of interestingness. So the average of this xj minus the average of the yj. And with those interestingness statistics, the TJs, with the TJ sigma 0 to sigma h, we will store them from the largest to the smallest. And this is the ordered statistics. So the idea here, or the intuition is that if the largest one happens to be the identity permutation, then this feature is likely to be interesting. Otherwise, if the largest one is from the permutation, then this feature is likely to be uninteresting. So that's the whole idea behind this procedure. So we define our contrast score accordingly. So we still have the difference contrast score or the maximum contrast score. For the difference contrast score, what we do is that if the largest one is the largest statistic is from the original data, then we take the difference between the maximum and the second maximum, call that a contrast score. So this is positive. Otherwise, if the maximum is from a permutation, then we reverse the order. We take the difference between the second maximum and the maximum, so we get a negative contrast score for this feature. And the maximum contrast score is defined in another way. So we always take the absolute value of the largest contrast score, but if this maximum is from the original data, we keep it as positive. Otherwise, we added a negative sign to make it negative. If there's a tie, that is the maximum and the second maximum are equal, we call it 0. So either way, we can define our contrast score. And here's an illustration. This is an interesting feature. So the original data, here it is. It has 2 replicates in the experimental condition, so n equals 2. 1 replicate under the background condition, so n equals 1. So we first calculate the degree of interestingness. So it's the average of these 2 minus this. So that's 5. Sorry, that's 8 minus 0. So we get an 8. And we permute it. So here we consider h equals 2 permutations. So essentially, you see that we either swap 0 with 6 or 0 with 10. And in these 2 cases, the degree of interestingness will be 5 minus 6, negative 1, 3 minus 10, negative 7. So we get 3 statistics here. Then we define the contrast score. For the difference, it will be the maximum minus the second minus maximum, so I get 9. And for the maximum here, clearly it's 8. And because it's from the original data, so we have a positive sign, so we get an 8. Now, an uninteresting feature. So from the original data, we get 2 minus 2, 0. And this is 2.5 minus 1, 1.5. 1.5 minus 3, negative 1.5. So we get those 3 statistics and we sort them. So the maximum is 1.5, but it's from permutation. So when we take the difference, 1.5 minus 0, we need to multiply a negative sign. So I get a difference as negative 1.5. For the maximum, here the maximum is 1.5, and we know it's from permutation. So we multiply it by a negative sign. So we get negative 1.5. So you see the difference between the uninteresting feature and the interesting feature in terms of their contrast scores. Okay, then with those contrast scores, how do we set a cutoff? So here, the BC procedure is not applicable for the general case when we have more than 1 permutation. So when H is greater than 1. And this is similar to the multiple knockoff case. So you have 1 original data, but multiple knockoffs. How do you set a threshold? So for this, we borrow the procedure from GZ. So here the idea is still you get the absolute non-zero contrast score values as candidate threshold. But when you consider the possible threshold, the numerator in the ratio is different. So you see this goes from 1 to 1 over H. This is also going from 1 to 1 over H. The reason is that we are having H negative controls. So we need to account for that. Again, we find the smallest positive threshold such that this ratio is under Q. And with this threshold denoted as TGV, we call discoveries as the features whose contrast scores are greater or equal than TGV. So to guarantee the theoretical FDR control, we need conditions for the contrast score as well. Here with those H negative controls, the second condition becomes that, okay, the contrast score is taking a sign of 1. This probability must be no greater than 1 over H plus 1. So you can imagine when it's equal to 1 over H plus 1, it just means that you have a uniform distribution of the H plus 1 statistics, right? So it's one of them are randomly picked as the maximum. So then for the original data to be picked as the maximum, that probability is only 1 over H plus 1 for uninteresting feature. And also for uninteresting features, its sign must be independent of its absolute value of contrast score. So we can show that our two ways of defining the contrast scores, in this case, satisfy these conditions. So finally, differential analysis. This is similar to the enrichment analysis with m doesn't equal n because we need permutation as the same. But what's different is that in the definition of the degree of interestingness, for enrichment, we just use the difference statistic. But for differential, we don't care about the sign. We don't care about the direction, which condition is bigger. So we take the absolute value of the difference statistic as our degree of interestingness. And we define contrast score as before, and we find the cutoff as before. So just to quickly show that if you recall for this feature, in the previous case, here we have 3 minus 5, that's -2, but now we change it to 2 because we take the absolute value in the degree of interestingness, and the contrast score is defined accordingly. And also here, so we don't have negative sign in the degree of interestingness anymore. All right, so with that, that's how our ChIP-seq framework would work for different analysis scenarios. Next, we're going to show some simulation to verify that our approach is indeed working and also has some advantages over existing approaches. So we'll consider enrichment analysis and differential analysis. And for the number of replicates, we consider many scenarios ranging from 1 versus 1 for enrichment analysis. So by the way, I need to say that the differential analysis cannot work for 1 versus 1. So we must have at least 2 replicates in one condition. But for the enrichment, we can do 1 versus 1. So 1 versus 1, 2 versus 1, 3 versus 3, or 10 versus 10. So we included this because this is the case when we can compare with the non-parametric test. And for the data generating distributions, we consider Gaussian, Poisson, or negative binomial, the 3 commonly used distributions in bioinformatics. And for the background, like how features behave when they're from the background condition, we consider homogeneous, which is favorable for the pooling approach, or heterogeneous, which is more realistic. And for the number of replicates, we consider 1,000 or 10,000. Okay, we compare our approach with the general approaches. So BH for thresholding paired for p-value calculation, or q-value paired with paired or pool. And also for local FDR, we consider using the empirical null based on Gaussian or the swapping empirical null. All right, this is the first set of results. So for the 1 versus 1 enrichment analysis, so as we expected, for the homogeneous assumption, so this is the condition where BH pool is supposed to work. And indeed, we noticed that when the feature number is not very large, although there's slight inflation in the actual FDR, y-axis compared to the target FDR, but it's not very off, so it's doing reasonable. But what's doing the worst is the 2S1. So if you mistaken a 2-sample test as a 1-sample test, as I said in the beginning, the p-values are totally off. And as a result, the actual FDR can be very high. But when we move to the heterogeneous scenario, so when the features do not have the same distribution under the background, then the pooling approach can do a poor job, while our paper can control the target FDR, control the actual FDR as a target FDR in all the cases. So now let's zoom in for target FDR equals 5% and compare the power. So here it is. So at 5%, we see that although pooling approach is advantageous in the homogeneous scenario, but under the heterogeneous scenario, it's doing very poorly. And we are doing the best. We are the most powerful method under the target FDR. And local FDR method for empirical Gaussian now, although it's controlling the FDR very well, at least in this case, but its power is not as high as ours. Now 3 versus 3. So here we consider a case with outliers, which means that we just, for the 3 replicates, we randomly add some number not from the same distribution as the 2 other measurements. So in this case, we can see that again, 2S1 is totally off. When there's no outlier, then we can see other methods are doing reasonable, but when there is outlier, and even assuming the correct Gaussian distribution to be the correct distribution, can have inflated FDR. And this is a fact of the parametric assumption. So clearly, when there's outlier, that parametric assumption doesn't hold. And now let's move on to the power comparison for 5% FDR. So again, we see that we control the FDR reasonably well, and we have very good power. So this is the case, which is very interesting, I would say. So 2 versus 1 with Poisson or negative binomial. So one thing I want to point out is that model misspecification definitely has some issues. So for example, here we consider Poisson to be misspecified by log normal, and the actual FDR is very off. Another thing worth pointing is in the negative binomial case. So when we correctly assume that the data come from negative binomial, but we know that negative binomial has 2 parameters, one for the mean, one for the variance or dispersion, depending on the definition. So for the second parameter, when it needs to be estimated, we just do that. And we have 3 points for estimating one negative binomial. So that makes the estimation very difficult. So by plugging the variance estimates into the negative binomial, we see that the actual FDR can be way off. So this means that even though you correctly assume the negative binomial here, with such a small sample size, the parametric model will not give you a very good answer. And again, we can control the FDR very well. And finally, comparing the power, we see that under the 5% target FDR, we are the most powerful, as before. So last comparison for 10 versus 10. So here we compare against the Wilcoxon rank sum test, the parametric test that assumes the correct distribution, Poisson negative binomial, and the permutation test. And we see that in this case, all the methods are doing reasonable, but still we are not insured for power, so which is very good. All right, so finally, I'm going to show some real data applications in the previous 4 motivating examples. And we're going to compare our Clipper framework against these cutting-edge bioinformatics tools designed specifically for each task. So for the p-calling, we picked that popular software Max in its version 2, the most recent version, and also Homer, which is another popular software for calling peaks. So we can see that one thing I need to mention is that although Max has that problematic p-value issue I mentioned before by mistaking a 2-sample test as a 1-sample test, but in fact, for its FDR control, it didn't use the p-values. What it used is by swapping the experimental condition and the background condition and control the empirical FDR or the FDP to a threshold. So that's why you see by looking at the green line for Max 2, its FDR control is not that bad. But clearly for target FDR less than 5%, it's not doing perfect. And for Homer, unfortunately, its actual FDR is way off. So what we did is that we implement Clipper as an add-on to each method. That is, we take some summary statistics output by each method, converting them into our contrast scores, and then apply Clipper for thresholding. So with that, we can see that we significantly reduce the FDR for each method. Looking at the power, so we see that for Max, for the part when its FDR is controlled, we're not sacrificing much power. And for Homer, this is the result. But since its original version cannot control FDR at all, so it doesn't worth putting it here. The second application for peptide identification from mass spectrometry data, this Mascot is a popular software. We see that its FDR control is actually okay. And we compare Clipper with it, and we find that under the FDR control, we have better power. The third case is for differential gene expression analysis. Again, we picked 2 popular softwares, DSeq2 and HR. To our surprise, DSeq2 cannot really control the FDR well, while HR can. And we also considered the 2 software's variance with the IHW by incorporating gene variances as a covariate to boost power. With that, we see that the change is not very obvious. Yeah, so then we compare the power with HR since DSeq2 cannot control the FDR well. So in this comparison, we see that for target FDR greater than 3%, we are more powerful than HR. And then we look into the reason why DSeq2 cannot really control FDR well. And here are 16 genes p-value distribution. So we use permutations to make those 16 genes non-differential. And then we apply DESeq2 to compute the p-value for each gene after each permutation. And we can see that surprisingly, these genes' p-value distributions are far from uniform. Instead, they have a node near 0. So that explains why they tend to be called out by DESeq2 as DEG, even though they are not. So that can explain the inflation in the FDR. Okay, this is the biological validation for the DE genes done by each method, including CRIPPR, DESeq, and HR on a real data set. And the short take-home message is that the DE genes done by CRIPPR is more biologically meaningful and interpretable. So we also applied CRIPPR to the cutting-edge single-cell RNA-seq data for DE analysis. So to obtain the truth here, we used our own group's simulator as a design tool. So I would say that advantage of the simulator is that it can preserve gene-gene correlation. So with this simulator, we actually find that, again, we can control the FDR and has the best power. So surprisingly, HR here cannot control the actual FDR. So I think it's likely due to the model assumption, the parametric model assumption that doesn't hold so well for single cell data. So that's why its power, although being the best, but given its FDR, so it's not really desirable. But among the methods that can control the FDR, including Will-Coston and t-test, we are most powerful. So finally, for the Hi-C data, we compare against 3 popular software, and the message is similar. Some methods cannot control the FDR at all, but compared to the method that can control the FDR, we still have some power advantage. So the take-home message is that we propose a general framework for the computational biology analysis where people are interested in marginal multiple testing for discoveries. And we just echo the message that sometimes we don't need p-values to achieve the goal. Because what we do is that by using the contrast scores to directly set a cutoff, we avoid the need for valid null distribution, either finite sample or asymptotic. And we don't need the high resolution p-values, which are needed by the BH or Q-value procedure for FDR control. And because the contrast score definition can vary, there are many choices that can satisfy the conditions for thresholding. So we think this framework will have broad applications in high-throughput data analysis in biomedical sciences. And also, we want to echo the importance of FDR control, even though this is a central topic in our statistics community. But I think in many bioinformatics methods, they simply assume the FDR is controlled without validation, and that's a serious issue. And for our future work, first, we want to incorporate some feature covariates to boost the power of paper, just like the IHW method did for p-values. And we want to find a more rational way for choosing the contrast score and the number of permutations for power consideration. And finally, we want to implement CRIPPR into software tools for specific tasks so people can start using this. So lastly, I want to say that related to this work, another recent work in my group for finding differential express genes along something we call pseudo time, you can consider the pseudo time trajectory inferred from single cell data. So in this tool, our motivation came from the fact that existing methods have p-values under the null, clearly not following uniform 0-1, as seen here. So that gave us the motivation to develop another tool. But I want to say that this is a similar issue in the field. So related to that, I want to say that another piece of work we did, or perspective article I wrote, is about the distinction between hypothesis multiple testing and binary classification. So in a collaborative work with cancer biologists, we just tackled the cancer gene prediction problem using binary classification instead of hypothesis testing, which was used a lot in the field. But the issue with multiple testing is that, if we go back here, they actually need some p-value combination before doing thresholding. And essentially, the p-value combination is often done by Fisher's method, which assumes independent p-values, and that can cause some issues. So that's why I will say that using binary classification formulation can simplify the problem greatly without addressing that. So we don't need to address that p-value combination difficult issue. So finally, I want to thank my PhD students who lead this work. and also the City of Hope collaborator who helped us generate a realistic benchmark data set for the FDR calculation in the mass spectrometry part. So for that part, we didn't use simulation, we used real data for benchmarking. And also for our collaborator, cancer biologist, Dr. Winnie at UC Irvine, who was an author of the Max paper. And I'm very appreciative that he acknowledged the issue with that software and discussed with us for this work. So thank you.
Thank you, Jessica. We're going to open it up to questions. Feel free to either post them in the chat or feel free to, if you feel comfortable, unmute yourself and ask it. I'll wait a few seconds, and if not, I have a specific question I'd ask. All right. Oh, I see William. Did you have a question?
Okay, so I'll ask a quick question. So I'm interested knowing, so the p-value usually a function of signal to noise ratio. So the formulation of the score is not obvious how the noise is accounted in the procedure. Can you give a little intuition?
That's a very good question. So I would say, not straightforwardly, but I would say that the noise is actually accounted for in the contrast score distribution. So this one, the thing we obtain. So each contrast score is an observed value of the random contrast score, right? In other words, so basically by pulling them together, this is very similar to the Efron's local FDR or empirical null part. So we're looking at them together. And so essentially, when our conditions are met, you would expect the distribution to have a symmetrical form on the left if we don't look at the right tail. So I think this is some way to verify, okay, this approach is working reasonably. And also, I would say that the randomness, all the randomness in the contrast score is actually considered in this thresholding procedure. So the validity of this procedure is based on the three assumptions here. So with that, we can show, okay, this can guarantee the frequentist FDR control. And essentially, you can consider this contrast score as a function or map of the p-value, because both the p-value and the contrast score are some summary of data, right, for every feature. So for that part, they're the same. But one thing the contrast score doesn't rely on is that it doesn't rely, so unlike the p-value, we require the p-value to have, each p-value to have a uniform 0 to 1 distribution under the null. But people don't usually check that. That's the problem. If you don't check that, then you cannot simply assume it holds. While for this one, so basically for a p-value check, if you want to do that, then you can plot all the d p-values in the plot, in the histogram, and you should expect to see, okay, there's a mode near 0 for the interesting ones, and it should be like roughly uniform for the remaining part. So if people do that, then it can sort of guarantee the p-value approach's validity. However, people just didn't do that. And they also need to spend so much efforts to get the p-value, to get high resolution p-value. For example, in bioinformatics, if the model is complicated, people need to rely on permutation to obtain the p-values. And that step is very computationally intensive. So what we want to argue here is that getting the p-values simply for FDR control is not necessary. So you can use this approach to control the FDR directly.
Thank you.
Thank you.
I think I have a follow-up question, but I will let Walter ask his.
Okay.
I saw Jian appear, so Jian, if you want to ask your question, I can save mine till after later. So.
Yeah, thanks, Walter. Yeah, Jessica, very nice talk. So I have actually follow-up question with William about your 3 assumptions of your contrast scores. Yeah. You have very general framework seems that, and your 3 assumptions seems very weak, so you don't need a very strong assumption.
Right.
My first question is that it seems like you still need some, it looks like your distributional plots previous page, that is actually, you need some assumption on the magnitude of the contrast score, right? So, but these 3 assumptions seems like there's no nothing to do with the magnitude.
So by magnitude, you mean like how large the range is?
Right, exactly. For this uninteresting like contrast score, it should be close to 0, right? So
for the okay, that's very good question. So I think ideally the distribution would like this. So you have a very concentrated distribution around 0, and you have a long right tail for the interesting.
Right.
So
right, that completely makes sense to me. Yeah, but in your 3 assumptions, it seems like I cannot read from your 3 assumptions.
The 3 assumptions will not guarantee the shape. You would not guarantee the, I would say, actually pick it back. So you will not guarantee on the, or you will not say anything about the magnitude as you pointed out. So that's why that 3 assumptions has nothing to say about the power. So when the distribution is really spread out and it makes the left tail and right tail hard to distinguish, in that case, using the procedure can still control the FDR, but the power will be very low.
I see.
Yeah.
I see. That makes sense. So do you have any theory or insight about the power based on this procedure, how you construct the contrast ratio to score, like to improve the power?
So I think our intuition is, this is still our ongoing work, but I would say our intuition is, as you said, we hope the contrast score for the uninteresting features to have small magnitude, but for the interesting features have a large positive value.
I see.
Yeah.
Thank you.
Thank you.
I guess I'll just ask my question quickly and then I'll let Will go. It's very so you mentioned it's not sort of ongoing work, but the question I keep coming back to is how to choose this contrast score, because it seems very general to Jian's point, but it seems like to me to Will's point, the p-value is nice because you have this sort of it encodes both the signal and noise sort of ratio aspects, but it seemed like you were using differences, and I'm just curious, like, how does one think about the optimal? Is there an optimal choice? Is there better? I mean, obviously you have choices that you want to be centered at 0 with a tail like you have here, but I'd assume that there might be things to do that are better than just taking differences. And have you thought about it? And what would be better choices than others?
Yeah, I would say we currently don't have a good answer. Yeah, but still, I think that's something we definitely need to think into. So like you said, we were motivated by the most powerful test in the testing framework, right? Like the Neyman-Pearson lemma, that sort of thing. But still, if we don't want to go any parametric approach, if we don't assume any model or distribution, that route will be difficult to pursue. So that's why I think empirically, I can say, okay, empirically for the enrichment analysis with equal number of replicates, our empirical observation is that the difference statistic works the best. But the difference may be taken after some transformation of data, like the log transformation, if you have count data, for example, like log the count +1, that kind of transformation. But for the enrichment with m doesn't equal n and the differential, which will require the permutation, for that part, our empirical observation is that the most powerful contrast score is to use the maximum. Yeah. But still, I want to say this is just empirical observation, and we still understand not enough.
It's still very helpful to hear the differences. Thank you.
Thank you.
William, do you have a follow-up? And then I guess we can thank Jessica. I don't know. Oh, you're muted.
Yeah. Actually, my question is similar. I think similar as Waters is you could define your C based on the Z-score or based on the raw effect. I was just curious if you see any difference when the noise will make a difference.
And definitely. Thank you for your insightful question, William. I would say, I want to mention one thing is that although the cases I'm showing here is very simple, right? We just do the sample mean, like you said, we didn't really consider other covariates or confounders to adjust for, but my intuition says that this framework can be applied to the regression framework. So for example, you could do regression and you could use the coefficient estimate to check as long as the 3 assumptions are met, then that coefficient estimate can itself be a contrast score candidate. So then in this case, if you know a test statistic is powerful, then we could borrow that test statistic to be our contrast score. We just want to avoid the p-value step.
Yeah, thank you.
Thank you.
Well, let's. I guess you know, virtually it's hard to thank Jessica, but we can I guess, do a round of applause for her somehow. I know there's an emotion. There we go. So we can do that. Thank you, Jessica, for the wonderful talk. We're gonna give you about 5 minutes to just take a breather, because and recover.
Okay.
But anyone who's interested can stay for the post-seminar discussion and continue discussing Jessica's work. So thank you all for coming, and thank you again, Jessica.
Thank you, everyone.
Hi, Jessica.
Hi, Walter.
It looks like I see two people here. So normally I let people who haven't chimed in yet chime in. It looks like everyone else. We've had a lot of Zoom fatigue recently, obviously, from the full year. So I'm not surprised that people might have dipped out. But I think there's two people.
These two are my students.
I was gonna say I don't recognize the names. That's why I was a little.
Because I encourage them to, because they work on this project. I encourage them to.
I see.
Yeah.
Yeah, no, we've had the last 2 weeks we've had a little bit of a drop off in the post seminar just because everyone's just I think zoomed out by this point. But I wanted to stick around and say thanks again. And I did have so you were saying this is my only, so I was just trying to understand one last thing about the project that I got confused about. So because you were saying empirically you're seeing different things, and of course it depends on how you standardize to get this like your choice. So it's sort of like you have a bunch of steps that can happen prior.
Prior to this.
Yeah, and I'm just curious, like, so I have two scientists who have the same data. They want to have FDR control, and they choose different scores, so they're going to get different results. So like, how does one go about presenting these results in terms of to science, like clinical, like on like more of a domain perspective, so less statistical procedure perspective, but more just like you go and you write a paper, you use this method Clipper in your domains. Like, how does one, because you have to now tell them exactly what score you used, and you have to tell them how you pre-processed, but do you also go about and say, this is exactly how we pre-processed and do sensitivity analysis around it? Like, I was just trying to think, like, how do I go to scientists and present this kind of approach?
So I would say it's similar to when you choose between possible models. Like you could do model, you could do linear mixed effect models, right? You could do logistic regression, or you could use another link function. So I would say it's the same as that you need to specify the contrast score you use, and the data pre-processing need to be described before applying Clipper. So of course we can, so what I have in mind for our future implementation or promotion of this is that we want to provide people with some graphical summary checks, so they can say, okay, given my input data, and I run Clipper to check whether the assumptions could seem to be reasonable. If not, I can try data transformation and then apply them to Clipper again. So as long as they pass the assumption check, then for the Clipper part, we can make it very clear that, okay, what's the contrast score you use? And people can just directly state those in their method section. So to make
and you're gonna, just so you know, you're gonna hear my dog go in a sec, because I think there's a dog around the corner. But the only other, so my only other follow-up was, because I was thinking like of a sort of a stable subset kind of thing. So like, because if I choose multiple contrast scores, so there's the pre-processing aspect, but there's also just, I choose multiple contrast scores and then I have slightly different sets that I'm going to produce. Like, I would assume most of them would overlap significantly. So I'd be looking for like a stable subset or something, but I guess you're not going to have any guarantees on it.
Basically, if you try multiple contrast scores and compare the discoveries, then to see which one give you the most, then you are in that p-hacking issue, right?
That's what I got. That was exactly. I'm like, so anywho.
So I would say in the future, I think what I envision is that we will give people default choices based on the analysis problem. So if we have more understanding about the power, which one's more powerful, then we will just give people that suggestion. So then they don't need to make a choice.
That makes sense.
Yeah.
Well, I think I have to go yell at my dog because he's currently outside barking at something, and I'm probably in trouble. So I need to go run and yell at him. But it was lovely to meet you, and thank you for the great talk. And tell your students they've done a great job, although they're currently muted and no video. So tell them a good job on this work. And I hope you enjoyed your visit.
Definitely. Yeah, it's a nice virtual visit. Thank you.
Of course. Thank you. Have a good rest of your day.
You too, Walter. Thank you.
Bye.